In previous sessions, we learned how to find the velocity from the graph of displacement versus time. In this session, we're going to learn how to get the displacement from the velocity versus time. The figure shows the velocity of a particle moving along the x-axis is plotted versus time. And the motion, as the graph shows, has three intervals. In the first interval, the particle increases its velocity up to 2 seconds, and from 2 seconds to 4 the velocity is constant, and then the velocity started to decrease in the last interval until it reached to 0 at time t equals 6 seconds. It is required to find the magnitude of the displacement, that is, the distance traveled by the particle between the time t equals 0 and 2 seconds at the first interval, and the second interval between 2 and 4 seconds. Also, it's required to find the magnitude of the total displacement, that is the total distance traveled by the particle for the first 6 seconds of its motion. Also, it's required to find an equation for the position of a particle as a function of time in the first motion from 0 to a, that is, in the time interval from t0 to 2 seconds. Now, determine the distance traveled in the first two intervals. Obviously, the area under the curve in each interval represent the distance required. This comes from the basic algebra, where the integral is going to be over dx from x initial to x final on the left hand side, while the right hand side from t initial to t final. For the integrand vx, that integration is over t. Of course, this equation comes from the definition of the instantaneous velocity, which is vx equal dx over dt. By solving the integral on the left hand side, we're going to get the displacement, and the right hand side represents the area under the curve for the time interval required. Now, for the first interval, the area under the curve is this red triangle. So the red triangle has an area of half the base multiplied by the latitude. The base is taken from the figure as 2 seconds, while the latitude is 10 meters per second. So the result of the distance in this interval is 10 meters. Similarly, for the second interval, the area under the curve turns out to be a rectangle, and this rectangle in blue has a base of 2 seconds and a latitude of 10 seconds by multiplying the base by the latitude. Well, to get the distance for the whole interval from t equals 0 to 6, we have to find the last area of the yellow triangle, which is half the base by the latitude, where the base is 2 seconds and the latitude is 10. So finding the area of this is going to give us 10 meters, and then we add up this area of 10 meters to the previous one of 10 and 20, then we'll get the total distance 40 meters. We can solve this problem by an alternative way, which is very much simpler than this one, by taking the area of trapezoid. The trapezoids have two bases, one with 2 seconds and the other with 6 seconds. If we apply the formula of half the sum of the bases multiplied by the latitude, we're going to get a similar answer of 40 meters in this method. To find an equation for x as a function of time for the first phase of the motion, we need at first to find the velocity for the straight lines from 0 to a. And this velocity is nothing more than the slope, the product of the slope and t. And the slope can be obtained from the graph, which is simply 10 divided by 2, that is 5. So if we substitute this 5 meter per second square in the equation, Vx turns out to be 5t. And then we're going to use this equation in the next step. By using this equation, I'm writing Vx as dx over dt, and from that we can get this integral on both sides, the one with the variable x and the other with the variable t. The limits for the variable x is from initial value of x 0 to x, while that for the time, the limits are from 0 to t. By conducting the integral, you're going to get an equation of x equal 2.5 t squared. That is the equation of the position of the particle. Well, we can solve this exercise by following the same method as before for the position of particle for the phase 1 to find the equation for x in the second phase. And the answer is given as this. And also we need to find an equation for x as a function of time as well for the first phase, and the answer is given as 30t minus 2.5t squared minus 50. To get an equation for the second phase of the motion from A to B, so we need to use the obtained equation in previous part, where x equal 2.5 t squared, and we substitute time t equal 2 as the start of the second phase. We're going to get an initial position of 10 meter. It's obviously the velocity at this phase is 10 meter per second. As it's known that the velocity of 10 seconds can be written as dx over dt equal 10, and then from here we'll do the same method as we've done before by integrating both sides of dx equal 10 dt from the left side from initial position of 10 meter up to x, and then the right hand side from time initial 2 seconds to time t. Then in this case we're going to get x on the left hand side, x minus x final, x minus x, that's x initial, that is x minus 10, and on the right hand side we're going to take you're going to get 10t minus 20, and that is the equation for the position in the second phase. So to find the equation for x as a function of time for the third phase from B to C, we need to make use of the last equation obtained for the second phase, that is x equal 10t minus 10. This is to find the initial position for the third stage, which is final position for the second. By substituting t equal 4 seconds, you're going to get xb equal 30 meters. And then from the slope of the straight line BC, we're going to get an acceleration and from the slope, and this slope gives us minus 5 meter per second square. Now the equation of line can be written as Vx equal V naught x minus 5t, where minus 5 represents the slope, which is the acceleration, and V naught x represents the velocity intercept in this case. So to find the velocity intercept, which is the initial velocity, what we have to do, we have to put V final equal 10, where the time is 4. By substituting the time and the v final, we're going to get v naught equal 30 meter per second, and then the equation of the velocity is equal 30 minus 5t. So we're going to use this velocity as before in order to get the position of the particle at this phase. Using the obtained velocity, Vx equal 30 meter per second minus 5 meter per second squared t, and writing the velocity as dx over dt from the definition, and then take the integration of both sides, the left side with respect to x and the left hand side with respect to t. The limits for the left hand side is from 30, the one we just obtained as the initial position, up to x, and the other limit is from tb equal 4 seconds up to t, which is the final time is equal to. By doing the integration, and then we're going to get x final as x equal 30t minus 2.5t square minus 50, and that is the answer.